So today I want to show how we can prove the soundness of type systems in Calc in the more traditional way. Amal showed us a relatively unusual way yesterday, and she contrasted it to an approach that involves such keywords as progress and preservation. I'm going to sort of reintroduce those ideas in Calc today and say a little bit more about the broader context of how they're not such a specialized proof method as you might think from the way that they're usually described. And I want to start out with a really simple example of a type system, which is one for this language, which is just a language with two types. It has the type of natural and the type of Booleans, and doesn't even have variables. That we won't need any typing context here. It has number constants, addition, Boolean constants, equality comparison, which I'll actually define only to work for numbers to keep this simpler. And finally, we have a general if statement where we have some Boolean condition, and depending on which way it turns out, true or false, we go into one of these two sub-expressions. And those can have either type. They can be numbers or they can be Booleans. So you could implement short-circuiting Boolean operators by desugaring them into if statements whose then and else cases are themselves Booleans. Right. And we can define a judgment that tells us which expressions are values. It's going to be exactly the constants, the number constants, and the Boolean constants. And we can define a small step semantics in pretty much the same style that I introduced in my previous lecture. I'm just showing three representative rules here. These are the rules that apply to the equals operator. And one rule, which is a little bit counterintuitive, it takes a while to get used to this style. If you have an equality whose two sides are constant numbers, then in one step, that goes to the result of comparing those two numbers. So I'm writing equals with a question mark on top of it to indicate some built-in equality testing operator that we actually run at this point. This isn't syntax. We actually want to check, are these equal? If so, we step to true. If they're not equal, then we step to false. Now, if we have an equality comparison where we're able to take a step in the left-hand operand, then we can take that step and change that operand, leave the right-hand operand alone. And similarly, if we're able to take a step in the right-hand operand, then we can push that step into a larger context where there's a left-hand part that stays the same under the assumption that the left-hand operand is itself a value. So this is enforcing a deterministic evaluation order, pretty similar to what we saw for a Chlipala value lambda calculus. Question?
Should it be plus or equals there on the bottom?
All right, I forgot an equals in the middle. Thank you. Okay. Any questions about this semantics before we start using it to state properties like type soundness? Assume all the natural rules are present for the other construct as well. And if you're wondering what exactly the natural rules are, this is a good time to ask. Yeah? I can't hear you, sorry. No, that's not what the rule says. It's n1 equals n2 is a piece of syntax, and this rule says how it steps. It's not, shouldn't read this as if n1 equals n2. All right, so we're going to define a type system for this language and prove that it's sound in an appropriate sense. And here's the full set of typing rules. We have that any number constant has type nat. So capital N nat is one of our two types. Any Boolean constant has type bool, where capital B bool is the other type. Furthermore, if two expressions are both nats and we combine them with plus, then that term has type nat. And if two expressions are both nats and we combine them with equals, then that term has type bool. And the last and maybe most interesting rule is for if, where if the test expression of the if, E1, has type bool, and each of the two cases, the then case and the else case, have some type tau, we don't constrain what tau is. It could be either nat or bool. The important thing is that both E2 and E3 have that same type. Then that type is the type of the overall if expression. So this acts sort of like the ternary question mark operator in C and Java and similar languages. And it's also exactly what you find in languages like ML and Haskell. All right, any questions about this type system before we state what it means for it to be sound and prove it? All right, so we saw the definition of type safety yesterday, and I'll just repeat it here. We will say that an expression I only showed a selection of the rules. You have to imagine that the other natural rules are also present there. So a term is going to be safe if we consider all other terms we could reach by 0 or more steps of execution from that term. And every one of those is either a value or it's not stuck. It's able to take a further step to some other term, which I've called E double prime here. So in other words, as long as we keep running, either we get to an answer or there's further computation that we can do. We're not stuck in some state, like for instance, if we tried to add true to false, then we would be stuck. Over here, we can see we'd be stuck if we ever got to an equals where there's a Boolean on one of the two sides. There'd be no rule that applies there, and that would be an example of a stuck state. And we're using this type system to rule out stuck states. Any program that passes these rules can never reach a stuck state. Actually, I think I'll take advantage of delaying turning on the projector to use this middle board also. So Amal talked about the standard approach to proving type sets, proving theorems like that, given the fact that E has a particular type. And it involves these two keywords of progress and preservation. But I'd like to state that proof strategy in a more general way and relate it to another one that we already saw and relate it to common proof strategies throughout different approaches to proofs about programs and verification and all that stuff. So basically, the type system is giving us an invariant that we can use to prove a property of a transition system. And invariants for transition systems are a very general idea. And the way this usually works is we have some sort of transition system that has a set of initial states. For this example, we can imagine that the initial states are all the well-typed programs. And then from those, we can somehow branch out and consider all sorts of different steps we could take in reaching all sorts of different other states. And this expands out from the initial states to the full set of reachable states in the transition system that we've defined. So there were some states we just say by definition are the ones we start in, and there are some rules that let us go from one state to another, and those rules define the full set of states that we're able to reach. And in this case, those arrows are just the small step relation here. So we start from any well-typed term, and we take any number of steps, and there's a well-defined notion of what is the full set of terms that we could reach through this process. For this language, it's already an infinite set, but mathematically it's completely well-defined. And we also have some set of states that are somehow bad. We want to make sure we never reach. And the important thing, oh, by the way, for this example, the bad states are exactly the stuck states, the states for terms that are not values and also cannot take a step. So the important thing is that there's this kind of alley in the middle, and we can see that the reachable states don't intersect with the bad states. And therefore, starting from the initial states, we'll never get anywhere bad. Often, it's a little tricky to prove this property directly. So what we might do is approximate the reachable states and head over and narrow this alley a little bit. And we're defining another state, or another set of states called the invariant. And as long as the invariant still doesn't intersect with the bad states, we can use it to do a proof that the bad states are unreachable. And there are three basic properties we have to prove to do that. One is that every initial state is also inside of the invariant. These properties are going to be sort of visually obvious from the way I've drawn it, but it's helpful to formalize them also. So every initial state is also contained within the invariant. And the invariant has no overlap with the bad states. Their intersection is empty. And also, I'll write this one kind of informally. The invariant is closed steps, meaning if you start out inside the bubble for the invariant and you take a step, no matter which step you pick, you're back inside the invariant somewhere. And so this is a very general strategy you see in program verification techniques like model checking also. We used it to verify a factorial state machine and a simple multi-threaded program in my second lecture. So this idea is at the heart of most techniques for formal proofs about the correctness of programs. And it just so happens that particular terminology historically is attached to it for type soundness proofs. In particular, we call this second condition the progress condition, and the third condition, the preservation condition. And we'll see exactly what those mean in the context of type systems in a moment. Yeah?
Is there a difference between type soundness and type safety?
I think those are usually used as synonyms. Right. So all this is pretty abstract at the point of these pictures. Yeah, question? I don't think there is a usual name for that because for type soundness, we tend to define initial and invariant to be the same set, so it would be too trivial to give it a name. But for other applications of this technique, they're different in interesting ways. Yeah?
So it seems like the definition of progress is more at any given point when you're not finished, you can make another step. Why does it seem to? I don't know. I'm having trouble when you find that with this definition.
The definition of bad is about not being able to make a step.
Oh.
So saying there's no intersection is a way of saying you can make a step. All right, so maybe it's time for me to roll the dice and turn on the projector and see if it overheats. Yeah.
Why do you use the word invariant for that? Is there some intuition or something like that?
I don't really know. Invariant is, I think, one of the standard terms of computer science. It's pretty much always used for this kind of thing. It was first defined maybe in the 60s or so. And yeah, so just by definition, that's what it's called. All right, so let's apply this idea to prove that this simple type system actually does guarantee program soundness or program safety. I'm starting here with just another copy of the transitive reflexive closure relation that I defined last time, which basically corresponds to when we take an arrow like this one and put a star superscript to mean we switch to considering 0 or more steps of the underlying arrow. So this is exactly the same definition as last time. And here is the definition of the syntax of this language corresponding to the grammar that I put up there. The value relation, the step relation, including the cases I didn't write up there. So I can flash any of these up that anyone's wondering about, but they're not too edifying. And here's our type system relation that, for instance, so it's a binary relation between expressions and types. And it, for instance, says any constant number expression is related to the type nat. If E1 and E2 are both related to nat, then plus E1, E2 is related to nat. Maybe the most interesting case is this last one for the if rule that says if E1 has type bool and E2 and E3 have some type T, we don't know what T is, we just know they agree on what their types are, then the if expression that puts them all together has the same type T. So I will process all these with calc and register all of their constructors as hints for the proof automation. And now we have these two conditions, progress and preservation, where progress corresponds to the fact that our invariant, which is basically, the invariant is the set of expressions E that have some type T, essentially. This invariant does not intersect the bad states because you can always take a step from any point in this invariant as long as you're not already a value. That's essentially what the progress condition says. Whenever E has a type, E is already a value or there exists E prime that E can step to. Yeah? You're asking why this is the right typing rule here?
No, I'm asking why it's called
Okay. As in has tie. Right. Okay, so how do we want to prove this progress condition? There aren't too many options given the way this is stated. Sorry? Let's do induction on the derivation that shows that E has type T. We can write that as induction 1, and I will do some of that too. So our first case is pretty easy. I'm not going to do that yet, but let's just look at this goal and make sure we believe it's true. In the first case, we use the first typing rule that says a number constant has type nat. And it requires us to show either a number constant is a value or something else. And of course, we know a number constant is a value, so we'll be able to prove this left-hand side of the OR. And indeed, E-auto will do that for us. Then we need to be able to show that either a plus expression is a value, it isn't, spoiler alert, and or there exists some other expression that it can step to. And we have these helpful premises that sort of enumerate a 2x2 space of possibilities about the status of the two arguments to plus. Either they're values or they are themselves able to step. So one thing we can do here is run the intuition tactic that's going to automatically do case analysis on which side each of these OR assumptions came from. So where we have 4 subgoals, it'll go up to 7 because we'll split this one subgoal into 4 cases. So in the first case, E1 and E2 are both values. So intuitively, how can we prove the goal in this case? Sorry? That's a little lower than the level of intuition that I'm aiming for. Like, well, why do we know that? It is true we want to go to the right-hand case. We can actually take a step here. Can someone else explain how we know that's true? Yeah.
There should be a rule that says that plus steps to the primitive plus option.
Yes, and indeed that rule is included. And okay, so how do we know we can use that rule here?
Because both E1 and E2 are values.
Okay, so for instance, let's do inversion on H1 and H2 and substitute any new variables that introduces. Oops, I'll have to do that separately. So now we have that this actually generated several cases, but in this case we have that E1 and E2 were both number constants. So we'll be able to see that this step fact does hold because the rule for adding 2 numbers is to just do the addition and create a new constant with the result of that addition. So E-auto handles that case just fine. But now we have a little bit of a problem. One of these cases of the inversions is adding a number to a Boolean. So how do we know that this is actually impossible, which it is? Yeah? Right, we can do inversion on H0. It turns out, if you look at those rules, there's actually no rule that shows that a Boolean has type nat. So we've come into an impossible case. So inversion takes care of that one. Similarly here, now it's H that says that a Boolean has type nat. We can invert that. And in this case, it's H1 and, it's H0 and H that say that. So we can pick either one and we get our contradiction. All right, so let's see, where are we in this process? Okay, so we handled the case where E1 and E2 are both values. We now have the case where E1 is a value, but E2 can take a step. And I'll actually use destruct to introduce a name for this existentially quantified variable E prime. I'll bring it into our context as a new free variable. Now we know it's X that E2 is able to step to. So is it the left-hand or the right-hand case of the OR here? It's the right-hand case because we can take the fact that E2 steps and use it to step this term to plus E1x because x is the thing E2 steps into. It's important we have this fact here that E1 is a value, otherwise that wouldn't work. And I didn't actually have to think that through because I think eauto can handle that pretty easily. And this case is symmetrical. Let's use destruct to introduce a name for the existentially quantified thing we know exists. And then that's enough to let us get eauto to do all that. And this one case left is actually a little redundant. We did more case analysis than we need. I can just do destruct on H1 again and ignore the fact that E2 steps because it isn't even E2's turn yet. All we need to know is that E1 steps, and we can use that there. So the logic of this is pretty similar for the other cases. So let's try to write some automation that's going to do these case analyses for us automatically and let eauto finish up in every case. So here's where we were here. One thing I'm going to do is instead of intros, I'm going to write intuition. So the very first thing we do is expand out the full set of cases. We'll get a moderate number. We have 16 cases considering all the ORs in all of our inductive hypotheses. And I'll run eauto afterwards so we get rid of any of the really easy ones. Doesn't look like there were any in that case. Intuition got the really easy ones, so that didn't help us. So I can delete this. So I'll write the actual code in LTAC, the proof automation language, to make this work. But do we have any suggestions of informal heuristics that we might apply to decide which of these inversions are useful to do at which points? Okay, so your suggestion is always do inversion on a value, on any hypothesis that says value. That, I think, is going to turn out to be fine here, because value is not defined recursively, so there will be no more premises generated of type value. Turns out that there's a what I found works here is a kind of combination of that with another rule. So here's what it is. If you proved that some expression is a value, and I'm writing this question mark variable to indicate pattern matching, we find some hypothesis, we'll call it H1, that says something is a value. And by the way, we also have another hypothesis that tells us the type of the same expression. If we see this, then we actually want to do inversion on both of them. Let's do inversion on H1, and actually I'm going to use a tactic I defined earlier called invert that combines some of these things that we're doing over and over again. It does the substitution, and it also clears the hypothesis. So we can invert H1 and also invert H2, and presumably some of these cases in the invert H2 will be impossible ones, like we saw below, where we knew, oh, this Boolean constant has type nat. If we do inversion on that, we see it's impossible, and those cases just get pruned away. So this should do something useful here if I've typed it right. Yeah, so that one, let's back up. It found that E2 has type nat, and E2 is a value, and it automatically inverted both of them. And we see here 16 subgoals. Afterward, there are also 16, because all the other cases we generated turned out to be impossible. And for now, I'll just copy and paste this so we can see it running again. Yeah. Sorry? The second one eliminates impossible cases, yeah. If we run this again, unsurprisingly, we'll see the same thing happen with E1 with the two assumptions about that one. All right, so that's working pretty well. Let's run that as many times as possible for every one of the subgoals. And then actually, I'll be optimistic and run eauto in every case that results and see how that goes. So now we're down to 20 goals, which is more than before, but we've done some extra case analysis, which has helped us make progress. All right, so any suggestions for another useful heuristic to use here? Sorry? Right, every time we see a hypothesis that says there exists something such that, let's automatically introduce a name for the thing that exists so we can use it in our further proofs. And I'll write that like this. If we know there exists X such that something, then let's use the struct to open up the exists and introduce a name for the thing that exists. Okay, so now we're down to just 7 sub-goals. This is great. We need to do something fundamentally different to make progress here. So we have to show an if is a value, which it isn't, or an if can make a step. And this if is applied to a constant Boolean. Yeah?
Is there a reason you didn't change the pattern map and the exists X binder?
Are you asking about the code at the precise point where the cursor is?
Yes.
You mean why didn't I put a question mark there? Because this is a locally bound variable that it wouldn't even make sense to mention anywhere else. In essence, we're saying there's an exists with some variable, and I'm going to call it X. It doesn't really matter what variable name the original hypothesis chose, because we can just alpha convert as necessary.
But it'll match even if it's like exists B.
Yeah, this is a binder, not an equality test. Yeah. I think I could, let's try it. I think I could write an underscore here, and it would be fine. 7, 7, yeah. Yeah. It's true. It'll bind any variable. That would actually be syntactically illegal to put a question mark there. You mean, right in this position, it is syntactically illegal to write a question mark. So the handling of variables is different from the handling of terms. The question marks are only for terms. This is a bound variable, whereas if a variable occurred here, it would be a free variable. And the two cases get different treatment. It binds to any term. It doesn't need to be an identifier.
Use an LPAC variable. X is a Boolean variable.
Also true. All right, so what can we do to make progress in this case? We're going to need to show that this if can take a step, but the rules don't apply directly. I didn't show you the rules, actually. The rules are if true reduces to the then case, if false reduces to the else case.
That's the context of the type of goal with Boolean, if Boolean B, and if it match this structure Boolean B.
Okay, let me try to translate that into a higher level description of a strategy. Did I hear someone else suggesting a rule also? It might have been the higher level description, if so. Inversion might help us here, but not, we don't have any hypotheses left to invert on, so we would have to do it on some of these variables, which would be a little tough. Yeah, so I haven't really introduced context properly yet, which is not why I'm not explaining it that way to begin with. That's how I'm going to use it, and I'll explain it as I type it. So the basic idea is we should notice, to make progress here, we need to know if B is true or false. So we're going to do case analysis on B. So let's do that manually first. Let's destruct B. Okay, so now we know that we have a Boolean that's true. Let me e-auto that one, because now the rule will tell us directly a true if reduces to its then case. And similarly, a false if reduces to its else case. So we can see in this case we had false, which makes it easy. So the rule that I'll add here is, as was suggested, I'm going to use a context pattern which says match some pattern at any subterm within the goal, not just for the overall conclusion that we're looking for. If we ever see an if on a Boolean, let's call it B, for any two arguments, that doesn't make sense, then let's do a case analysis on that Boolean. And there's actually one important thing we need to do here, otherwise it loops forever, as it's doing right now. There are a few ways we can fix that. One of them is something like, if this is a variable, then fail or destruct. Is this going to work? Failed too much. Sorry, if it is a variable, then we destruct. I made that more complicated than it needs to be. Only apply this rule if b is a variable, because if we've already run this rule, it will say true or false, and we don't want to keep destructing that forever. Otherwise, we'd be in an infinite loop. And now the proof is done. Let me delete all that stuff. Yeah?
Sorry, is bar B is actually like a tactic of some sort? Or
It's a tactic that succeeds only when the argument really is a variable.
okay, so those chains, they only keep going to the next tactic and previous tactic succeeded?
Yeah.
But otherwise, it doesn't change your context and goals at all.
Right. You run it only for the potential side effect of giving up in this branch of the proof search process. All right. I think it's in the implementation of calc, so I can't easily show you where it's defined. You couldn't do it. Yeah, you see, you can implement it with more primitive features, but it's a little uninformative how it works. You can write it. You can write it yourself, but it's nicer to have it built in. Yeah. So I'm going to give a name to this tactic so we can mention the same set of rules again and cross our fingers and hope they work for other things. So now with that naming, we can just say induction 1t, and that gets proved. All right, so that was condition 1, which says when an expression is well-typed, it's not stuck. Condition 2 says when a well-typed expression steps, the result is also well-typed, in fact, at the same type as the original. It turns out it's okay for the expression to step to a new expression that's well-typed at a different type. The proof will still work. But the stronger form is also true, and it's sort of informative to see it, and we need the stronger form to get the induction to go through. Once the induction is done, we can forget the fact that the same type holds after the step. So we have two hypotheses that are proved with inductive definitions. Any guesses which one we'd like to do induction on?
Induction 2.
I think that's the wrong guess, unfortunately. By process of elimination, that leaves induction 1. I think that this proof works out nicely if we do induction on the step. It is actually an inductive judgment because these two rules appeal recursively to the same kind of step. And we need to use induction on that structure to get this proof to go through. So let's optimistically see how this goes. All right, 9 subgoals. I don't remember how many may have been pruned already, but here we are looking at a case where we have a plus of 2 numbers and it has a type. And we want to show that the number that results from adding those two has the same type. So what could we do here? We could do inversion on this hypothesis H, and I'll write it as invert to get some of the extra stuff for free. And we know, by looking at those rules, the only type that a plus could ever have is nat. So therefore, that'll tell us t is a nat, and this t will change to nat, and then this becomes very easy to prove using the n has type nat rule. Invert does invert gives nicer looking goals. And it also clears the hypothesis. So you can pretend invert is the primitive that you would use by default. It's defined at the top of this file. It does a little extra work. All right, so we're going to need in general in this proof to do inversions of this kind. But if we ever have, yeah.
Could you explain why does eAuto have trouble applying inversions? Seems like it's
We could make it imply inversions, but the thing is, eAuto in general is going to consider a vocabulary of proof steps you might run at each stage of a tree, searching through different proofs. And it tries all the different ways to order those steps. And if you had 2 different inversions, you'd get the same result no matter which order you ran those steps in. And that would blow up the proof tree exponentially, and it would be a performance challenge to get that to work nicely. There is syntax, which I might show at some point here or in a later lecture, to let you suggest arbitrary new proof steps, and you could suggest inversion. In practice, things tend to work with a forward step, applying simplifications to the hypotheses like inversion, and then a backward step using something like eAuto to search for all proof trees that use different kinds of steps.
okay. Cool.
Okay. So it would be a mistake potentially to say whenever you see a has-tie hypothesis, do inversion on it, because in some cases you might wind up producing an infinite tree of inversions where you had has-tie on a variable, and then you learn that variable has to be a plus, and then you do inversion on the typing assumptions for each of the two arguments to plus. One of those turns out to be maybe a plus, and you just go on like that forever. So I'm going to use a simple heuristic here that will help us avoid that gotcha. I'll say whenever you find a has-tie, don't just do this, don't just run inversion. I'm going to run invert1, which is another tactic defined at the top of this file, which you'll be able to see later, that only succeeds if inversion prunes the cases to just one possibility. So this turns out to be a safe thing to do. I believe it doesn't break the previous proof either, which is nice. And then we can try this, and that proves the rest of this. Yeah?
When you applied the auto there, it wasn't applying the constructor as
It was. Definitely was, but we don't have any other lemmas about has-tie. So all these proofs are working via the constructors of it.
So then when you inverted on that assumption that has-tie plus number, wasn't that, I thought that was the constructor.
No, inversion is, well, so that's definitely reasoning in terms of the constructors of has-tie. If that's your question, then the answer is yes.
I guess I just don't remember whether the constructor was giving us that from number n1, number n2, we get number n1 plus n2, where the pluses are mathematical version plus is well-typed, where it's using our plus within our terms.
Well, so there are two different judgments here. The small step, I. The small step is the one that tells us, in the case we were looking at, that we've taken two numbers with a plus around them and changed it into one number with a plus. And then we did a separate inversion on a typing judgment whose arguments were determined by which step rule we had used. I don't know if that explanation helps. Maybe we should take this offline. All right, so the conclusion of this is pretty straightforward. I'm going to register both progress and preservation as hints, and then the argument that Amal did informally on the board yesterday that combines these into the main type safety property is so straightforward, we don't need to give any other advice. We just state it. We say, if in 0 or more steps you get from E1 to E2, and E1 had type T, then either E2 is a value or it can step somewhere. This follows very directly from what we've already proved, and maybe just E-auto alone will do it. Nope, we need a little more help. Maybe we need another hint also here. We run T and, sorry, this does need induction. We do need to do induction on the derivation of this multi-step relation. And then E-auto does the rest. Turns out the two theorems we proved are basically just the base case and the recursive case, so that's why it goes through so easily. Yeah?
So both times, but if you probably delayed the introduction of T earlier on.
Yeah.
So did you, I assume that makes it proof easier?
It does. So in general, when you do induction, I mentioned this rule before, but it's a counterintuitive thing that bears repeating. When you do induction, all the variables that are quantified before the thing you're inducting on remain, in some sense, you never get to pick those values. They're sort of fixed in each of the proof cases. They're given to you, and you must work with them. All the variables that appear later remain as for all quantified in the induction hypotheses, and you get to choose those every time you use the induction hypothesis. And in this case, if we're ever dealing with expressions of different types than the original type, which is very true, for instance, for equality, we started out with a bool and we need to deal with subterms of type nat, then it's important to be able to choose the right value of that variable as we invoke the induction hypotheses. And postponing quantifiers lets us do that. All right, so before I run this command to close the book on the arithmetic module forever, any more questions on these proofs? Okay. So the natural next step is to adapt this methodology to the simply typed lambda calculus. We saw a proof for essentially this language by a different method yesterday. Here's our language. Just to keep it interesting, I picked one base type of natural numbers, as in this example, and I just gave the natural numbers constants and one plus operator. And then besides that, we have the usual variables and Lambda abstraction and application that we have in any Lambda calculus. And then our values are either constants with numbers inside or they're Lambda abstractions. And I define the usual substitution operator. It's not too interesting to dwell on the details. And I'm going to, in the last version I did the kind of simple small step semantics. And for Lambda calculus, I'm going to use the evaluation context that we saw last time. So these are this is basically a grammar of expressions where the expression has a single hole in it that we're going to fill in with another expression. And the plug relation captures the rule for what is the result of plugging a value in for the hole. So the really simplest case is if you have a hole, you put E inside it, the result is E. And similarly, if you have a context that has some subcontext and the left-hand argument of a plus, the right-hand argument is E2. If you plug in E for the hole, you should see what happens when you plug E into the subcontext C. You get some E prime, and then you make that the first argument of the resulting plus, and you keep as the second argument the value that was given here. Yeah?
Could subs have been a relation? And are there pros and cons to doing it one way or the other?
It turns out that for these proofs, the definition of subst, I think, doesn't matter.
Okay.
The proof is completely parametric in subst, so I went with the simple recursive definition, whereas plug, writing it as a relation makes eauto much more effective. The proof actually does depend on the details of how plug is defined.
I see. So when you're reasoning about the structure of plug, it's better when it's relation instead of function?
Yes, so eauto in general, its primitive ingredients are sort of defining rules of relations. So
Okay.
it's very prepared to understand how plug works.
I see.
Yeah?
Can you in the prompt was using the mechanical keyboard not do that? Someone's using the keyboard at prompt.
Oh, it wasn't a question for me, sorry.
Can you maybe not use the keyboard?
Oh, sorry.
Thank you.
Okay. So this plug definition is essentially the same as the one from last time, except it has the extra plus cases added. And I won't dwell on those here. Actually, let's give some more space to this. So we define our fundamental relation of the main kinds of reductions that happen in this language. We can apply a lambda to a value, and that steps using substitution. And we can apply plus to two constants, and that steps to a new constant, that is the addition of the original two. And we can wrap that in another step relation, which says, if we have some context and we plug E1 into it, then that steps to the same context with E2 plugged into it, as long as E1 steps to E2 in terms of this more basic relation. It's not super essential to follow all the details of this because proof search is going to plug in most of the plumbing for us. But this is basically the same style as last time. I introduced an extra relation step 0 because now we have two kinds of primitive steps, the function step and the addition step, whereas before we had just one, and it made more sense to inline it into the definition of step. So now we have a type of types, very similar to what we just saw in Peter's lecture. We have a type of natural numbers and a type constructor that, given two types, builds the type of functions between those two, between that domain and that range. And we're going to need to work with typing contexts, as we've seen many times before in other parts of the summer school. And how do people feel about whether I should write up on the board the typing rules for simply typed lambda calculus, or is it ingrained in your minds by now? Okay, I think I'll refrain from doing it then. So I'm going to use this notation empty to stand for a typing context that contains no variables. Notation is different from a traditional definition because it's basically a macro that gets expanded everywhere you use it. I'm going to represent typing contexts as functions from variable names to either none when the variable is not present, or some of a type when the variable is present. And an empty context maps everything to none, so that's what this means. And here's another function, override, that we're going to use to take a context, which is a function from a string to an optional type. And we're going to override the value of variable x to be type t. So this is a new function that checks if its argument is equal to the variable you're overriding. If so, we return sum of the new type t. Otherwise, we return the mapping of the original typing context. So with that, we can now write this typing judgment, and I'll make some more space for it because it does fit on one screen, I think. Yeah. So now our typing judgment is a three-place relation. It has the typing context as the first argument. And typing context, again, is a function from strings or variable names to optional types. It tells us what is the type of each variable that we have in scope. We also have an expression and a type, like in the previous simpler example. So what is the type of a variable? It's what we get when we look up the variable x in the typing context and find it is there, so it's mapped to a sum, and the argument of sum is the type t that this variable has. Any constant has type nat, independently of the context. If E1 and E2 have type nat in a context, then plus of E1 and E2 has type nat. The Lambda abstraction case is more interesting. If we're trying to prove that this abstraction has this function type, what we do is we modify our typing context, overriding the type of the variable x that the lambda binds, and say it equals the domain type of the function that we're building. And then we check that the body has the range type of the function. This is pretty similar to something Peter showed us with a different encoding of variables in typing context than this one. And finally, if E1 has this function type, E2 has the domain type of that function, and then the application of E1 to E2 has the range type of that function. So the only perhaps surprising thing here is this particular notation for overriding, adding a new binding to a context here, and the fact that we look up in a context to do the variable case. Otherwise, this should map very directly to what we've seen on the board a number of times for simply typed lambda calculus. But any questions about that encoding before I start putting it to use? Okay. So I'm going to add hints for all the constructors of these 5 judgments that we've just defined. And now we're back to proving progress and preservation. I'll warn you in advance, it's going to take a little longer to get them to go through this time. But we can be optimistic and try to copy what worked last time. And we just need to fix this up to account for the change in the number of arguments that some of these things take. We don't even have this anymore, so that's nice. And let's try that. All right, so the top-level inductive structure will also be the same for each of these, but we'll need a few extra lemmas. So and I'm going to start using, instead of induction, I'll use induct, which is another fancier version defined at the top of this file, which in particular, what it'll do that the other version won't be able to do is here we have has type, where one of the 3 arguments is not a variable, it's a specific value, it's empty. And regular induction will get confused if one of the arguments to the predicate you're inducting on is not a variable. So induct is more clever about that and makes it work just how you want. Yeah?
Are these versions of invert and induct just basically generally useful variations on inversion?
Yeah.
Okay, they're not specific to this file.
They're not specific to this file, no.
Do you have like a package where I can use them?
Maybe someday. Right, so let's do fancy induction on the first premise, the first and only premise, the typing derivation. And I'll run t afterwards, and we'll see how far we get. 7 cases left, which I think is substantially less than the full breadth of cases that we need to worry about. This one says that if we take a step, that E2 is able to take a step. E2 is the second argument to plus. The first argument is conveniently already a value. So we know this is not a value. Plus is never a value. So we must be able to prove this, showing that plus of a constant to E2 is able to get somewhere. And that is, it sort of seems intuitively obvious that we have a step and we can push it inside the second argument to plus. But can anyone explain why this doesn't follow directly from the definition of step? Step was defined in terms of finding an evaluation context inside of which one of the 2 primitive reductions can happen. So why wouldn't this apply directly with Iato? It's buried another level deeper, right? So I can do inversion on H, and we'll see exactly what this step really consists of. We have some context such that a primitive step happens from E1 to E0, and we can substitute those two terms inside of our context, and we get E2 and X, which are the two things that we need to be using down here. And the problem is, let's be optimistic about this. I'll run a few commands that you don't usually need if you're doing automated proofs, but write says, when you're trying to prove an OR, focus on proving the right-hand side. So let's do that. And I think the thing that exists that we'll step to is going to be plus const and E2 goes to X here, so it should be X. We want to show this. And I can run eConstructor to use the one rule for step. And the first thing we need to do is find some context such that we plug something into it and we get a plus. And up here, we have a context such that we plug something into it and we get E2, one of the two arguments of that. Does eauto know this one? I think that would be too easy. Just use eauto here. It would probably pick whole for that context and get something too general. We just run this, probably doomed proof effort through. Yeah, here we're stuck because this is asking for a step 0, which is one of the primitive steps. It would only work if both sides of this were constants. And on the right-hand side, we have a non-constant that is actually able to take a step. So the challenge here is which context could we use to show that this step is possible? The context C from our premise is actually not the right one. It doesn't apply directly. Let me just check. Does eauto do this one? Yeah, eauto does that one. So it's good to understand a little bit of what it's doing. Can anyone have an idea which context we're actually using to show that this step is possible? We have C, and we need to use it to prove this fact here. We need to wrap an extra plus around the outside of the context. That's exactly right. So in particular, I think I could say apply step with, and I can give the context here. I probably called it C. I'll make it an E applied just to be safe. C equals, we have a plus 2 context that has a const n on one side and a whole, or actually has this context C on the other side. Now we need to show that when we plug some value into this hole, we get this value. And we can see, to make that work, if we plug E2 in here, if we plug E1 in here, we know that plugging E1 in C gets us to E2, which is exactly what we need here. We don't have to think about that too hard. We can just run eauto here, and that gets plugged in, and it all just happens to work out nicely. That's just one of our assumptions. Yeah. So that was a quick manual look at this case, but we don't actually need to think too hard about it because eauto knows how to do this case, or maybe not. Maybe it needs a higher number. Yeah, I need to increase the depth of the proof trees that it's searching. So I suppose that's the only reason we saw this case when we ran eauto at first. Does it need 7? Okay, it only needs 6 in this case, but we might bump that up a little bit just to be prepared for other cases. All right, so what did we do here? We saw that we had a step, and we needed to do inversion on it to expose all this stuff that we know about the definition of step. So I'm going to put in a general rule here to invert any step predicate. Let's see how this goes. And let's say we'll try eauto 7 now. Okay, good. So this one's relatively easy. The next one turns out to need a few more lemmas to go through, at least the way that I put it before it does. Maybe we'll find a better proof in the course of the next 25 minutes. The default is 5. Actually, now I'm curious, would 6 do it? Yeah, okay. We might need more later, though, so I'll even go up to 8. So increasing the bound unnecessarily could make your proof take longer as it explores unfruitful paths that go off in all kinds of directions. But increasing the number will never cause a proof that worked before to stop working, given infinite time in memory at least, which maybe some of you are lucky enough to have. It is depth first search. Right, if it were breadth first, then it wouldn't matter as long as we knew everything was true. Okay, let's prove preservation. So like before, what this is going to take is induction on the first hypothesis. So let's see how that turns out. So what happened here? And actually, it doesn't need induction. Let's remember, step is actually a single constructor rule with no recursive premises. So we could even just run destruct here, and it'll be just as good. So this basically just expanded out the definition of step in the theorem statement. We took some primitive step 0 step from E1 to E2, and then we lifted that step inside the context C. And we need to show that the result of the context of filling the hole in that context with the result of our small step really has the type we need it to have. So this really can be reduced to two sub-lemmas for two key parts of the proof. Any suggestions what one of those lemmas would be? One of them is a pretty easy one that doesn't even need any additional induction. It has to do with the step 0 hypothesis that we have. What would be a useful thing to prove about step 0? Right, so I'm going to copy this theorem statement and just add a 0 to it, and that will become the first of our main lemmas. I'll call it preservation 0 and say we're taking a step 0. So step 0 is the version that doesn't bother with evaluation context. It only encodes the two primitive kinds of steps you can take. So we'll do a case analysis on how the step went down and then call this automation. And then this looks like it should work fine, but the thing that's gotten us stuck here is that we haven't used simple anywhere. And simple will we use the definition of substitution to, I guess the substitution doesn't help us here. Yeah, so this is actually a case that we're not prepared to deal with immediately. Simplifying doesn't have any effect. We're not substituting inside a constant. Rather, a constant is the thing that we're substituting inside some other term. We're filling it in for a variable x. And I'm actually not sure. Okay, so I think this case, the case analysis gives us two cases. One of them is the case for lambda abstraction, and that one's kind of tough. I'll use the syntax to run t on the case for plus, and that one is completely eliminated. We get stuck in the case for lambda abstraction, and let me do this a little more manually to avoid some of these unnecessary case splits that the T tactic was doing. Let's invert on H0. Now this is fundamentally what we're stuck trying to prove. Actually, one more step. Let's invert H4 because we know exactly which term we're dealing with. And there's just one rule that applies there, so we can get like this. Okay, so we know that V is a closed value that has type T1. And we know that E has type T in a typing context where X has type T1. So if we substitute V for X in E, then that had better have type T. This might look familiar to those of you who've seen type soundness proofs before. This suggests another basic lemma that we'll need to prove with induction and apply here. Any ideas what that lemma is? It's usually called substitution. So informally, what does it say? Maybe it's kind of a dumb question because it says this. So let's copy this. Let's prove a lemma called substitution. And I think we're going to want to, I'll just keep the same variable names from here for simplicity. Let's see if this works. I also need x. So we have this derivation that e has a certain type, and it depends on the presence of a variable. We're going to substitute a known value for that variable. The known value we substitute has the right type. That should then tell us that the result of substitution has the type that we're looking for, with no further requirements that variables are present. And I'm going to do that by induction on the second premise here, which is this has type here, which kind of makes sense because we have a substitution that's substituting something inside of E, and this has type judgment is going to follow the structure of E, and we'll need that to know the way that substitution evaluates. See how that goes? All right, so this case is easier than it looks. We're stuck on testing. So this is actually the first time where we depend on the definition of substitution. So I shouldn't have quite said it was an opaque definition that would not impact the proof before. This is where it matters. We're stuck on deciding whether some two variables x0 and x are equal. And we can use the struct to do that case analysis. I'm going to run subst afterward, which in the equals case will just unify these variables and replace one of them with the other everywhere. So now we have to show that v has type t, when we know v has type t1, but we also know in the typing context where x has type t1, the type of x is t, which kind of tells us that t1 and t have to be the same thing. Let me prove that one with a lemma, something like this. We have a context and a variable and a type, and we override the context with that variable and then look up the variable again and get some other type, then the two types are the same. And we can do this by unfolding override, and then we can do a case analysis on string dec. We actually know which case it's going to be, but it's convenient to structure the proof this way. Unfold substitutes the definition of an identifier in place of that identifier. Yeah. So I'm going to put override same up here. And actually what I'm going to do is put it all the way up here with the definition of our tactic. And I'm going to do two things. First, let's find any time that we use string dec, which is the function for checking if strings are equal. I'll just automatically do this case split on the result of that test. And I'm also going to look for hypotheses in which I can apply override same, the lemma we just proved. So I'll use that to replace this hypothesis with an equality, at which point substitution can simplify the goal even further. So now we should be able to get farther along in this proof. For some reason it didn't do that substitution because I didn't ask it to. I'll just add subst here. So now it should really do automatically everything we did manually before. We have the case where x0 is not equal to x. So what do you think the corresponding rule for override will be in that case? Where x0 is not equal to x, we've done an override on x, then we then look up x0. What do we know about this type t that comes out? It's the mapping from the original context, and that will turn out to be contradictory here because empty has no mappings. So we'll get to that by proving a lemma that is the override different lemma. We have x and y, and it turns out x is not equal to y, then g of y equals t prime, or the sum of t prime. And I have to write x and y instead, maybe, or is it y and x? So let's try this. Let's try to use congruence to prove that side condition about inequality, and then we won't need substitution anymore. Oh, sorry, I forgot to change the name of this. All right, so let's see how that goes. Okay, so we got rid of that case we were stuck on, which was the case for, I think it was the variable case of the typing rule. Yeah.
Is adding the cases for the same and diff lemmas that we just proved to the LPAC, is that different than just adding them as hints for eauto?
eauto wouldn't apply them directly.
Okay.
eauto looks for a lemma that can prove directly the conclusion formula that you see below the double line. And those lemmas don't have the right form to apply directly to a has-tie conclusion. So eauto wouldn't use them for us.
Okay.
Yeah.
So the hints is for the eauto then? Sorry,
Hints are for eauto, yeah.
Sorry, what's in the
eauto is the tactic that tries all proof trees up to a certain depth built using a set of primitive steps that you've declared with hint commands. All right, so what do we need here? We won't need any of this stuff that I dropped in there. So we're trying to show that an lambda abstraction has a function type. So the first step is pretty easy. We can apply the constructor, precisely the typing rule over there. It'll give us one extra proof obligation, which is that when we override empty with a particular type, then we see that then the body has the appropriate range type of the function. But we're not actually going to be able to make progress here with our induction hypothesis, which is how we'd like to prove this. That only tells us about the type of something that is in an empty typing context. Here we have an extra value added in, so this doesn't apply directly. And actually, we want to use our hypothesis H0, which is very close. It says E1 has type T2. That's exactly what we need here, except up here we have this overridden typing context that happens. We've overridden the same variable x twice, first time with T1 and the second time with T0. So what do you think? Does H0 actually establish the conclusion that we're looking for? Yeah, it does actually prove what we need, because we can show that the effect of overriding a single variable twice is the same as just overriding it with the second value that you choose. When we override x with T0 here, that writes on top of the effect of writing x with T1 here. So we can prove that these are the same. And one nice way to get that to work here is to prove a fact about overriding twice. Let's say we have some context in a variable and two types. If we override the result of overriding, this is the same as just doing it once. I forgot to do something here. Type T2 is type string, or value T2. Got it. And okay. The way I'm going to prove this is I'm going to use, it turns out both of these results of override are functions, and I'm going to use an axiom that says two functions are equal if they return equal outputs on equal inputs, and I'll assign the name y to the inputs, and then unfold the definition of override, and then use our T tactic to consider all the cases. And then I'm going to make some more space here and add this as a rewrite rule that will be applied automatically. And now this subgoal almost goes away, but I need to actually change our automation to take advantage of the rewrite rule. So let me do this. First I'll copy this lemma out to its own spot here instead of being nested inside of the other proof. And then I'm going to change the definition of T and add one more case here where we try to use the auto rewrite tactic with the default hint database everywhere. And progress says this fails if it does nothing, so we don't get an infinite loop of doing 0 rewrites each time. Because when you have no further constraints, then you don't need them. You can just write an underscore. All right, so with that rewrite hint added, we should get further now. Now there's just one subgoal left. And this is the one where we need to use the induction hypothesis. Now we use eConstructor. We want to show that E1, the result of this substitution has this type, but we're a little stuck because the induction hypothesis only applies when the typing context is empty, and now we need it to apply in a case where the typing context has this one mapping in it. So what does that mean about how we should change our proof? When your induction hypothesis doesn't apply, what do you often need to go back and do? You need to strengthen the induction hypothesis. Yeah, that generalizes another way of putting it. I'm going to change this to apply to overriding any typing context, not just the empty one. Now we're going to get one extra case here where we have to show that if we have a typing fact that holds in the empty context, then it also holds in any other context. And yeah, I'm thinking I might switch to the completely filled in proof at this point, just so we're sure to get to the end. So why don't I go do that, and I'll show you the way that this turns out in the version I filled in already. Here's the substitution lemma. This is a key fact that we need, that if we have that typing holds in one context G, and we have some other G prime that is somehow a superset of G, namely every mapping in G is also in G prime, then we can lift this and decide that the same typing relation holds in the larger context. And that's a fairly straightforward thing to prove, and that's what we need to handle that one case we were stuck in. I have one other kind of silly looking lemma here saying if some typing fact holds in a context, then it also holds in another context that equals the original one. This is one of those funny lemmas that's useful precisely to guide eAuto, because it takes a transformation on the goal and phrases it in a lemma style that eAuto knows how to use as one of the steps that it considers in building proof trees. So with that, and here's another funky rule that uses a command called hint extern that lets you give an arbitrary tactic that is considered as one of the steps in building proof trees. And this one, I'm not sure if I could have done this as a lemma, but it was shortest to write it in this way. It proves a particular equality between override terms. And with that, this is now the statement of the substitution lemma that we had arrived at. And now it goes through automatically with those hints around. And with substitution as a hint, then this preservation 0 goes through. Then there's one more property that we need. Let's see, I think I might have hidden up here one other thing, ingredient that's important. I also define an operation for composing two evaluation contexts together, which turns out to be useful for the later stages of the proof, I think. And what this is going to do is give us a context that, if we want a way to rewrite, if we have some context C1, we're plugging into it the result of plugging something into C2. We'd like to be able to say that's equal to the composition of C1 and C2 applied to E. And so this is a recursive definition of a function that implements that kind of composition. And there's also a theorem saying that it really behaves the way you want. If you plug using the composed context, it's the same as plugging first with C2 and then plugging with C1 using the result of that. And this is useful here. Now that I think, I'm not sure this actually is necessary here, because you never know when you write these hints whether they're being used or not. I might have happened to do a simpler proof in the lecture just now that doesn't need this, but it's at least an interesting operation to be aware of, the existence of. But we were basically done with the proof down here. There's one more fact we proved, which is maybe a little hard to state in English, which is basically that if you have two terms, E1 and E2, that have the same type, namely for any type, if one has it, then the other has it, then that same description applies to the result of plugging them both into the same context. So two type equivalent terms going into one context produce two type equivalent terms. That's what this theorem says, and it's a straightforward proof by induction on one of these two plug relations. So once we add that as a hint, then we get the preservation lemma pretty straightforwardly. And then safety follows the same way as before, because progress and preservation are basically the base case and the inductive case of the proof of safety. Let's see if I have anything else to say there. Yeah, that's basically this soundness proof. I know there were a lot of details squeezed in there at the end. I think this is a good development to spend some time poking around after the lecture. But are there any questions I could answer in the meantime? Yeah.
Whenever you, in the previous file, whenever you added kind of a manual autocall in the tree for any context that doesn't match anything else, what was the extra bit on the end doing? Is that kind of using
Actually, I need to resolve what you just said a little better to something specific. Can you?
Sure. Could you go back to the line?
Let's look at the version I was editing before, then it's probably... Is this the version you meant?
Yes, this is the one that you were doing in class. Yeah. So with the with core in star, is that doing kind of using the hint database at wherever it's called? Or
Core is the name of a hint database. For some reason, auto rewrite always requires a name of a database explicitly as an argument. eauto can take a database name too. It's core by default for eauto. So this is rewriting everywhere using the hints that have been declared.
but it's using like dynamic scope, correct? So it uses the hint database at the point at which you call it.
Exactly, yeah. Just like eauto does.
Okay.
It uses the latest hint database value, not the version that was current at the point where you may have defined the tactic that says eauto in it. Any other questions? Yeah.
Can you suggest any preferences maybe for like better understanding the way Coq like automates things and thinks about proof trees and hint databases and all this automation wizardry?
Yeah, so my book, Certified Programming with Dependent Types, tries to explain all those things. More questions? Yeah.
So there's an incredible amount of detail that is embodied in the proofs that Coq is making. And I'm wondering, sort of in the social context, this is a very standard proof for simply typed Lambda calculus type safety. But you must apply Coq in a lot of situations where people have done sort of manual proofs of things, very likely without this much care taken. How often do you find that those are broken? That those proofs that are staged are broken by doing this? This is really a social question rather than
If that you really means me, then I just don't tend to do that kind of thing very much. To try to translate a proof on paper, I sort of think of all proofs on paper as proof sketches.
right.
So I don't bother with them.
Well, sort of the experience of the community. The community that's using Coq, I don't know.
So you're basically asking, how common is it to find a mistake in a proof on paper when you mechanize it?
When you go to the trouble.
Other people can answer that question better than I can. I think it's reasonably common. I don't have a number in mind for how frequent it is. Yes?
What is the number argument of hint extend to? So when you
Yeah, that I don't want to go into here, but you can see the Coq reference manual for the details. Yeah?
In the reverse direction from the previous question, is it useful sometimes, and this may be obvious, whether it is or not, to do a proof summary based on a detailed proof, taking intuition or not? Or is it just
What would the summary say? I don't quite understand the proposal.
like a set of exercises to fill in for a student or something to figure out the details? Or it could just be a set of steps that aren't every
So it's useful to divide a proof into lemmas.
Yeah.
I think the lemma statements are a good granularity of explanation for structure.
And then how do you decide what size lemma?
Based on a mental model of what your audience will understand. All right, so the hands-on exercise I'm going to suggest for later this afternoon is to add some extra features to the programming language that's being handled here and try to adapt this proof. It takes a very small number of lines to make this work, to make these proofs work for a new language, but it takes some practice to come up with those lines instantly, so I hope it'll be a useful exercise. Okay, thank you.
Specific features.
I will post information on that, yeah. Thanks.